Welcome. I'm Felix Hottenstein, the Sales Director for MSS Optical Sorters, and we would like to discuss with you today and present to you a guide to selecting the best sensor and sorting methods for your MRF. The way we'll go about it is we'll talk a little bit and introduce you to the CP-MSS system design process for a MRF. We will then talk a little bit about how, when, and why we use optical sorting and how it can be best applied. In the first main section of the presentation, we would like to discuss and show you in what applications conventional optical sorters can be used in MRFs. Then we'll get into the thick of things of where we think there is currently a big confusion within the industry when it comes to comparing conventional optical sorters with their near-infrared color and metal detectors with the robotic and artificial intelligence-based systems. The goal of the presentation is to present a technology platform that combines and fusions the different types of sensor technologies available with the most appropriate extraction technology. In the second main part of this presentation, we'll have a closer look of how artificial intelligence sensors and near-infrared technology compare and where they could be best applied or not applied. And last but not least, we'll have an in-depth look at comparing robotic extraction technologies versus air jets and how they compare against each other in MRF applications. Okay, let's talk about the system design process that MSS and the CP group have been championing for the last few years as far as MRF design is concerned. And the first step, as always, and we've had separate webinars on this particular topic, is the fractionation part, which means the sizing. In your typical MRF, this would normally include the sorting out of the cardboard and removal of the fines, 2" minus where most of the glass is located. The middle fraction sometimes, especially for larger MRFs, can be split up further as well, but sizing is always the first step in any of our MRF designs. The second step is the liberation, where we take the previously sized fractions and further mechanically sort them using air separation technology or 2D, 3D separators, etc. The main goal is to prepare all material streams for the downstream separation section, which is where all the optical sorting technologies are located. It is this third step that the rest of the presentation today will focus on. We'll do a deeper dive into the different smart and sensor-based technologies that are available today to make your MRF run as efficiently and with as little manpower as possible. For a quick visualization of those three principles that we just talked about, here is an overview design of one of our recent MRF installations, and I would like to show you where in those designs the three different steps take place. You can see in the upper right corner the loader filling the metering bin and then inclining the material up into the sort system. And in that first section, you can see a few screens, which is where the fractionation occurs. The separation section of the MRF is located immediately beside the fractionation portion, shown right here. In the remaining area of the MRF is where the separation happens. And again, this is where we use our sensor technologies to separate the mechanically pre-processed materials into all the final commodities. A second overview illustration of those three design principles are shown in this particular system. You can see in the front center the infeed area from where the material is conveyed towards the upper right into the fractionation section. In this particular design, the liberation section consists of an anti-wrap screen and a CP screen. Both these devices have the main function of separating the 2D fiber from the 3D containers. The separation section is again highlighted in yellow here, and this is where the final sorting of all the different container fractions as well as the fiber commodities occur. And this is where we will focus our attention for the rest of this presentation. So let's talk a little bit about when and why optical sorting technology makes most sense in MRFs. And we would like to make it clear that we don't really think it matters what kind of sensors you use for the detection or what kind of extraction method you use to separate the different types of commodities. We would still all put it under the umbrella optical sorting. One of the main points we always discuss with our customers is how can we add value to your generated commodities by adding an optical sorter. Secondly, can we use optical sorters to improve your quality? Or can we improve your quantity that you can process through the whole MRF? And furthermore, can we improve the consistency of your generated commodities so you can make sure you generate the same high quality commodities at all times? The hottest topic with our customers has definitely been the challenge of finding and retaining manual labor. And this is definitely where optical sorting technology in one way or another is able to assist. And last but not least, the use of optical sorters or any other smart technologies will improve the environment for your workers in regard to safety, as there is less of a need for them to touch and physically sort materials. Let's take some time and look at the different sensor technologies we use in what we would call conventional sensor technologies. And in the MRF applications, it's essentially three types. It's near infrared, where we can identify and sort different types of materials, such as different polymers or different paper grades. We can use color, which in MRFs is mostly used for sorting brown cardboard on the paper side, and natural from colored HDPE on the container side. The third sensor technology listed here is the induction metal detection, which in MRF applications we normally use on the fiber side to remove any metal contaminants in the fiber, or on the container side from preventing aluminum cans being ejected with PET bottles. For those of you who are not super familiar with how conventional optical sorters work, I would like to show this little animation of what it looks like. And essentially, you have a fast-moving conveyor belt where the material is nicely spread out and hopefully not overlapping too much, and then goes through a sensing zone where the different properties of the material going through are measured and analyzed, and then the algorithms, and based on your software setup, then decide which items are going to be ejected. In this particular case, the blue and the yellow bottles versus what is being passed through the sensor. As far as the actual configuration is concerned, what you see in the animation here is what we call a single eject setup. In other words, one set of air ejectors generates two output fractions, one positively sorted one and one negatively passed one from one input stream. For certain specific applications, we also offer a so-called dual eject configuration, where two rows of air ejectors generate two positively ejected fractions and one negative pass fraction from one input stream. Let's have a look at some typical applications in MRFs where the conventional optical sorters can play out their strengths. And these are mostly high volume applications where thousands of items have to be sorted out every minute. On the fiber side, we normally look at three different applications. Number one would be the primary sort of newspaper, mixed paper, and OCC. The second one would be the quality control of newspaper and mixed paper. And the third one would possibly be optional sorting of cardboard from fiber and containers out of the prohibitives stream. On the container side, the main application is definitely the primary sorting of PET, HDPE, polypropylene or mixed plastics, as well as the cartons. We do use optical sorters for secondary color sorting of HDPE, as well as quality control of PET, HDPE, and polypropylene or mixed plastics. Last but not least, we have installed our optical sorters on residue lines to recover any residual recyclables that might still be in that residue stream. I'm going to dive in a little deeper into the different applications on the fiber side, for which we use our FIBERMAX optical sorter, of which you can see a 3D rendering here. The main advantage of the FIBERMAX is its speed. We run the acceleration conveyor at 1,000 feet a minute and use a patented air assist system and eject hood geometry to make sure the material travels through the sensing zone and ejection area without any turbulence. Let's look at some examples out in the field. This particular FIBERMAX was installed after a newspaper screen to clean up the generated larger two-dimensional fraction. You can see the material right here, which consists of newspaper and some contamination that we're trying to remove. The detection and ejection zone, where the materials travel through and then ejected based on the settings in software. In this particular instance, we are removing all the prohibitives, which include containers and other non-fiber materials. Here is a closer look at the ejected stream. You can clearly see a lot of plastic film, aluminum cans, plastic bottles, and other random non-fiber items coming off the optical source. What is left clean is stream of contaminants and prohibitives. In this second example, we're going to take a look at a FIBERMAX configuration that we see more and more. In this particular case, we actually poly-eject the mixed paper from the screen that was generated by the 2D, 3D separator upstream. These streams further down the line tend to have a lot of contamination in it, with several items that we would deem unsortable. For example, black plastics, bottles that have water or ice in them, or other items that the sensor can just not detect. In this particular case, positively sorting out the mixed paper provides a very clean stream that does not have to be quality controlled. What is left over are the prohibitives, containers, and other contaminants that were in the original dimensional stream coming off the last 2D, 3D separator. As you can see, there's very little loss of fiber in this particular stream as well. In this last example of the FIBERMAX technology, we're going to be looking at a configuration where we sort out the prohibitives, so again the container and the residue, and the cardboard individually and separately from the newspaper stream. So this is the dual eject configuration that I mentioned earlier on in the presentation. And in this particular case, we have the up eject category being the cardboard. The down eject category is the prohibitives, so everything that is non-fiber. And then we have the mixed paper going through into the pass fraction. You can see the final OCC product right here, and please note that it was generated without any manual quality control. You can see the ejected prohibitives right here. Again, this would be anything that is not fiber, including film, containers, and any other contaminants. After removing both the cardboard and the prohibitives, you can see the final mixed paper quality that was produced by the FIBERMAX. Let me now move over to container line applications where we use the PLASTICMAX for all the high volume sortation. From a sensor standpoint, it's exactly the same as the FIBERMAX, but it's differently packaged to match the requirements of sorting containers. Like before, let's look at a few video clips. This particular example would be a primary sorter for HDPE, and you can see the input being spread out and metered into the unit using a vibratory feeder, the high-speed acceleration conveyor, the sensing zone, as well as the ejection hood. From this single eject configuration, let's go over to an example for a dual eject configuration. In this particular case, we would like to show the color sorting capabilities of the FIBERMAX unit. We have the up eject, the HDPE natural and white, down eject any fiber that is still left in the container line, and the pass-through would be all other plastics, including PET, HDPE color, and mixed plastics. Here is the takeaway conveyor with the ejected mixed paper. And up ejected HDPE natural and white. So this concludes our main first section of the presentation, where we talked about the various applications for our conventional optical sorters for high volume sorting applications. But now let's turn our attention to the second main topic of this presentation, and probably one of the main reasons why most of you tuned in, and that is robotic sorting and artificial intelligence. And we believe that within our industry, currently there's quite a big confusion where artificial intelligence is grouped with robotic sorting technology, and we are trying to push back against that because that doesn't necessarily always have to be the case, and in certain instances actively goes against what would be best for the application. Just the other day, I got a newsletter from one of the vendors of robotic sorting systems, and it announced that they were going to provide a new dose of robotic intelligence. And I was thinking, well, maybe we should look into robotic intelligence ourselves. And so we went out and got ourselves a robot. Of course, we mounted it into a support structure so nobody would get hurt. And then we turned it on to see what the robotic intelligence could do. And of course, as you can guess, nothing happened. So obviously, while the robotic portion was present, the intelligence was definitely missing. So where could we find such intelligence? Maybe even an artificial one. So we bought some books, and wouldn't you believe it, in chapter 12, the first paragraph, it says, "People often mistake robotics for AI, but robotics are different from AI. Artificial intelligence aims to find solutions to some difficult problems related to human abilities. Robotics aims to use machines to perform tasks in the physical world in a partially or completely automated way." And this is one of the main messages of this presentation. Robotics are not AI, and AI is not robotics. Or in other words, the relationship status is somewhat complicated. Or to say it even more explicit, we are of the firm belief that the sensing technology needs to be completely decoupled from the extraction technology itself. As far as sensors go, so far during this presentation, we talked about NIR, color, and metal. And on the extraction side, we talked about air jets with the conventional optical sorter and the suction on the robots. But what if you needed a different sensor technology to identify the targeted items in a mixed material stream? Or what if you needed a different extraction method in order to physically remove that item? Some of the additional sensor technologies within our industry are shown here, whether it's a 3D profiler, artificial intelligence, watermark detection technology, UV tracers, various X-ray technologies, and LIBs. Not all of them would probably apply to MRF applications, but some of them could and possibly will very soon in the future. There is no single sensor technology out there that can do it all. It either requires multiple ones or multiple ones combined together to perform the detection tasks that we're looking for. On the extraction side, not only do we want to make these different types of sensors work with just air jets and suction, but other extraction methods such as clamps, diverters, electromagnets, etc. So what is needed is a technology platform that allows you to pick the correct type of sensor with the appropriate extraction method and fuse them or marry them together for the perfect sorting equipment for your application. So the one thing you absolutely want to make sure is to talk to a vendor that offers multiple options so that you can truly pick the best one for you. So let's talk a little bit about artificial intelligence or AI technology. Based on all the articles that have been coming out over the last year or 18 months or even 2 years, we are made to believe that it is the solution to everything. So many parties within our industry, whether it's media, consultants, customers, system integrators, manufacturers, investors, and recycling organizations are pushing and promoting AI as the end-all be-all. Have you ever seen an article about AI for our industry that at least looks a little more critically at it? I sure haven't. And there are quite a few things that AI cannot do, and some of those we'll go into a little later on, but it surprises me that those issues are not discussed more often. In one way, it reminds me a little bit about all the hype on cryptocurrency. Only a few truly understand artificial intelligence. Many think they do understand it, but really don't. And most everybody else just hops on the bandwagon because they fear of missing out. To take it back to the title of this presentation, let's look a little more in detail on the pros and cons of NIR sensors versus AI sensors for MRF applications. I created this table to look at a few key properties between the two sensor technologies. The first one is machine width. The current standard for near-infrared sensors is that they can go up to 112 inches wide or 2.8 meters. With AI sensors, we haven't seen them go wider than 60 inches or 1.5 meters. So if you would like to go wider, you need to double up on your sensor. The conveyor and decision speed is probably one of the main differences between the two technologies. With the NIR, we can go up to 1,000 feet per minute without any problems. AI currently has difficulty going up to about 300 feet per minute. The decision speed is also quite significantly different, with the NIR being about 10 times faster between detection and decision to eject or pick up something. As far as material identification is concerned, the NIR sensor can truly sense what type of material a certain item is. The AI is doing it similarly to a human, where it simply tries to deduct what it might be based on what it looks like. But it can never truly measure what type of material it actually is. Both NIR and AI have the capabilities to provide a vast amount of data and statistics for monitoring purposes to the plant operator. There are obviously areas where the AI has some advantages over the NIR, and those are listed at the bottom of this table here. One of them is obviously the deep learning capabilities, the granularity down to which one can take the classification of individual product categories. But I won't be spending any more time with those three topics because they have been covered extensively by recent articles and webinars within the industry. Instead, I'm going to spend a few minutes on the polymer classification challenge, where we are made to believe that AI has similar capabilities to the AI, but it really doesn't. Start with an easy one. You can see two different types of bright orange detergent bottles on a shelf in the supermarket, and it's not easy to tell what polymer they are, but a trained eye can tell that the one on the left is PET and the one on the right HDPE, based on the patterns from the injection molding and blow molding process. However, once these items have gone through the use at the consumer, the collection, the compactor truck, and the handling on the tip floor in the MRF, they're not going to be as shiny anymore. They're going to be compacted or flattened, and it's going to be very difficult for an AI sensor to pick up the difference. A near-infrared sensor will not have any problems doing that whatsoever. Let's look at some trickier ones, like these two cups, and it would be very difficult for a person or AI to discern that the one on the left is polypropylene and the one on the right is PET. Or these two lids, where it's basically impossible to tell that the one on the left is polyethylene and the one on the right is polypropylene. Or these two thermoforms, where the one on the left is polyethylene and the one on the right is polypropylene. Or these two coffee cups, where the one on the left is polypropylene and the one on the right is ABS. As everybody knows, there's more and more black plastics in the input stream as well. And an AI or a human cannot tell the difference between those two thermoforms, where the one on the left is PET and the one on the right is polypropylene. A lot of research and development has gone into making black colorants that are detectable in the near infrared. And so those units will not have a problem distinguishing these two items, but an AI or a human would not have any chance of knowing that the one on the left is polypropylene and then the one on the right is polyethylene. The last item I would like to show are aluminum cans that have shrink sleeves on them that are made out of PET. A person or an AI-based sensor is not able to tell the difference between those and the ones that have the graphics printed right on them. However, any near-infrared sensor will be able to pick those up without any problems. Having said all that, I would like to go back to the slide that I showed earlier and to point out that it really makes sense to analyze all the different sensor technologies that may work best for your particular application. And sometimes it may be one particular one of all the ones that are listed here, or possibly a combination of all of them, but not necessarily just NIR or just AI or just color, but possibly other ones or a combination of multiples of them. So now that we've talked about the pros and cons of near-infrared versus AI, let's get into the last part of the presentation where we're going to discuss the differences between robots or suction versus air jets. And to emphasize again, just like we've been trying to explain over the course of this presentation, we're now really just looking at the extraction methods and the differences between them. The first parameter I would like to discuss is the effective picks per minute. And that doesn't mean the number of picks that in theory could be performed, but the ones that are actually being achieved by the respective extraction method. When we talk about air jets, based on the data that we have available from all our installations, we're able to achieve over 1,000 picks per minute over a 112-inch wide acceleration belt. It looks a little bit like multiple people playing the piano at one time. If you compare it to a robot, which in its best time can achieve maybe 60 effective picks per minute, it looks more like a cat playing with one paw, and essentially be more than 15 times slower than a machine with air jets. One of the other challenges that robots have is that they are limited in how many items they can pick at any one time. So if the material that they targeted is nicely spread out within the stream that's coming by, it's no problem picking those up. However, if the targeted items are all of a sudden all bunched up, or the percentage of the targeted items in the input stream increases either permanently or just temporarily, the robot is not able to pick up all the targeted items, which leads to either your pass stream being unnecessarily contaminated or the recovery rate of the targeted items being a lot lower. The next point of the discussion should be the geometry of the effector that is attached to the robotic arm, or as we would like to call it, more like the in-effector. Most of the ones that are out in the industry these days have what I'm showing here on the left, kind of a bellows type suction cup, and that would be the same whether the robot is a Delta style, multi-axis, or gantry. Based on everything we've seen out there in the different facilities, and we have seen a lot of them, these kind of suction cups are just not very effective. As you can see in the video on the right, they are missing targeted items left and right all the time. And we believe that has a lot to do with the actual shape of the targeted commodities that are being picked. And sometimes the suction cups just don't stand a chance. So for example, here on the left side, you have a carton, which is very two-dimensional and very flat, and it can be picked up very easily. However, the two items on the right, in this case natural HDPE and colored HDPE, are very three-dimensional in shape and are very difficult to pick up with a very small suction cup. Air jets, on the other hand, wouldn't have any issues with any of these three types of items to eject them properly where they're supposed to go. Something similar goes with the quality control of aluminum cans from the eddy current. If you have cat food cans that you would like to remove, if one of those cans comes upside down with the flat surface against the suction cup, no problem picking it up. If it's flipped upside down with this very three-dimensional shape against the suction cup, there's just no way it's going to be able to pick it up. Other items that are tricky for suction cups to pick up are small three-dimensional items like the pill bottles or the coffee pods, especially if they still have content in them. So maybe it's time for the design of the suction cup to be optimized so it can actually be effective at least a little more than the standard suction cup out there on the market. So how about we bring the floppy disk back? On our own robot in our shop, we have been testing a more floppy disk style suction cup, and as you can see from the video on the right, it works really well. Whether it's crinkled PET bottles or very three-dimensional HDPE natural bottles, it's being able to pick those up without any issues. So if you really want to or need to use suction to sort your materials, use at least a suction cup that works better. One of the things we've looked at a little more in detail recently is the comparison of cost per pick between robots with suction cups, robots with the floppy disk, or air jets. For this little exercise, we're assuming that the robots can actually generate 80 picks per minute. It would use about 1 suction cup per day per shift, which seems to be the average on when we talk to customers, or 1 floppy disk per day per shift, and that power costs approximately 10 cents per kilowatt hour. And so we're going to look at the cost of the wear parts, so the suction cup or disk, or the valves in the case of the air jets, and the CFM required to run the robots and the air jets. In case of the suction cups, the wear parts average to about 0.075 cents per pick and about 0.04 cents per pick on the CFM for a total of about 0.115 cents per pick. The floppy disks are actually about an order of magnitude less expensive than the suction cups. So while the CFM cost per pick remains the same, overall it drops to about a third of the cost per pick. So now when we look at the air jets, where we can do up to 1,000 picks per minute, and with the newest generation valves, which are very durable, you're only going to need or replace about 6 valves per year per shift, your cost per pick drop even more. To simplify it a little bit, the cost per pick with the floppy disk is about 3 times lower versus a suction cup and about 11 times lower when using the air jets. Now those cent values may not look like very much, but let's look at how much it costs to sort out a ton of targeted materials. So for example, for natural HDPE, we'll use about 7.5 bottles per pound, or about 16,500 bottles per ton, which calculates to about $19 spent for every ton HDPE natural sorted. Now that may be not too bad. It's about 1% of the current value, but still it's 11 times more compared to when being picked with air jets. One of the commodities that is widely discussed within the industry right now is polypropylene. So let's look at what the calculation looks with that particular commodity. If we assume there are 20 tubs and lids per pound, it will require 44,000 picks to generate a ton of material, and therefore it'll cost $50 to pick those items for the whole ton, which at the current prices is almost 10% of the value of the bale, and again about 11 times more compared to when this commodity would be picked with air jets. When we look at conveyor speeds and the difference between airjet sorters and robots, it is quite a significant difference. The airjet sorters, as you saw earlier, on the plastics we normally use about 500 feet per minute. On the paper we can go up to 1,000 feet per minute. The robots seem to be doing okay at speeds between 150 and 250 feet per minute, but anything much faster they have difficulties keeping up. As far as conveyor widths is concerned, as you saw earlier, the airjet sorters can get really wide, 112 to 120 inches in some instances. But robots are more limited With the Delta robots, you're around 42 to 48 inches width. Gantry-style robots can go wider, but then they become slower and can perform fewer picks per minute. So in general, if you need to go wider, you may require multiple robots, which then may be cost prohibitive, because if you have to purchase 2 robots for that same money, you can buy a much faster optical sorter. To summarize this section of the presentation, when we compare suction versus air jets efficiency, it is clear that the air jets are much superior. Whatever kind of sensor we utilize, the air jets are able to achieve 92 to 95% removal efficiency at any day of the week. Robotic arms that use the suction effectors that we discussed earlier are quite a bit less efficient, normally in the 65 to 70% range. If that was the case for air jet sorters, we would be laughed out of the room. So whenever you purchase a robot with a suction system, please ask for performance guarantees. Now that you heard me going off on robots for quite a while versus the air jet sorters, one of the things that the robots definitely have going for them is the ability to sort multiple fractions at once. With air jet sorters, we normally recommend just a single eject configuration. In certain specific applications, like you saw earlier in the presentation, we can go to dual eject. But with a robotic arm, you can sort 3 to 4 positive fractions at the same time without any issues. So as a quick summary of comparing the robot's suction systems versus air jets, we talked about the picks per minute, where the air jets are much faster than the robots. 2D shaped material sorts well with air jets as well as robots. 3D shaped material sorts much better with air jets. The effectors of the robots currently are still subpar to the positive pressure of the air jets. Cost per pick, air jets about 11 times less than the conventional suction cups that are used today. Conveyor widths and conveyor speeds are much better with air jets. The 2 areas where the robots do have an advantage, as mentioned a little while ago, are multiple sorts at once and the ease of retrofits into existing facilities. So let me try now to bring this all back around. When we started this conversation of talking about near-infrared versus AI, air jets versus robots, how about we look at a solution that combines 2 of the sensors, AI and near-infrared, with 2 of the extraction methods. What you can see here shown in our lab is that we used information from different sensors and then used them with different extraction methods. One of the examples we tested was the quality control of PET while sorting the thermoforms from the bottles at the same time. You can see in the video on the right that the robotic arm is picking the minority fractions, which in this particular case were aluminum and cartons, and the air jets are actually sorting the thermoforms, because the robotic arm could simply not keep up with sorting all 3 of those items from each other. The air jets are absolutely required to generate that additional 3rd fraction. Another such application is the quality control and color sorting of HDPE, where again the robotic are the minority fractions of aluminum and cartons, and the air jets are actually color sorting the HDPE, because it would be way too much work for one robotic arm to keep up. So we would like to emphasize one more time that we really need to try to separate the sensor technology from the extraction method. What we need to do is pick the correct sensor for the correct identification and then the best extraction method that works with that. Sometimes it may be near infrared with air jets, sometimes it may be AI with just air jets. And depending on what application it might be, maybe sometimes it'll be a metal detector with a suction cup. But we really recommend you talk to a vendor who offers multiple options so you can select the best one for your needs. And please ask for performance guarantees, because this is really where the rubber meets the road. I know this was a long presentation, but I hope we were able to give you a little bit of insight on how we approach the selection of different sensor technologies and how to pair them with the appropriate extraction methods.